Hello again. This is Math 1120 coming to you from the College of DuPage. The title of this lecture is Simple Harmonic Motion and such. As always, please be an active learner as you watch this video. An object such as a vibrating guitar string or the swinging pendulum of a grandfather clock repeats the same motion over and over. Refer to such motion as periodic motion or oscillation. A mechanical system that undergoes periodic motion always has a stable equilibrium position. When it's moved away from this position and released, a force comes into play to pull it back toward equilibrium. By the time it gets there, it has picked up some kinetic energy, and so it overshoots, stopping somewhere on the other side, and then again is pulled back towards equilibrium. If this cycle repeats over and over, we say the motion is periodic. Here are some examples. If you take a tuning fork and get it vibrating like this, the vibrations will hit the molecules, pushing the molecules closer together, but they will then push other molecules and fall back. So what happens is you have this, these vibrations are a clustering of molecules and a relaxing of the molecules. Pushing, falling back, pushing, falling back, pushing, falling back. Eventually this hits the ear and you hear the sound. But what you hear is the energy hits the ear. So it's not really the molecules other than moving in this longitudinal fashion. These are longitudinal waves because the direction or the velocity of the wave is parallel to the movement of the particles. Sound waves are longitudinal waves. If we move one end of a spring back and forth, continuously keeping the other end fixed, a longitudinal wave travels the length of the spring. And so you can see it gets tied together, far apart, tied together, far apart. Again, the wave moves along the spring, not the particles themselves. Longitudinal waves have compressions, that's where they get compressed together, and refractions, that's where they spread apart. Longitudinal waves can be generated in solids, liquids, and gases, and we know that sound always has to have a medium. In space, no one can see you scream. So here is a picture showing the compressions and refractions of the spring model. So there's a compression, and there's a refraction, there's compression, there's a refraction. But when you go from the same point in the wave to the same point in the wave, we call that a wavelength. So a wavelength is a distance like this, and is a distance like this. Now, if you measure not the wave itself, but the pressure that happens, there's a high pressure here, a low pressure here, a higher pressure here, a lower pressure here, and so on and so forth. So you see what happens with the pressure is it gets high, and then it gets low, and then it gets higher again, and then it gets lower again, and so on and so forth. Often, what you see when people are talking about sound waves is measuring the pressure. This is how microphones work, for example. So often, you will see a wave like this, which is a sine wave representing a sound wave. And we have other terms that are used here as well. We can talk about the amplitude of a sound wave. That's the distance from the equilibrium point to an extreme point. Notice that's also the difference from this equilibrium point to the extreme point. You also have a time period. That's from the same point in the wave to the same identical point in the wave. That's called the time period. That's called the period. And we also talk about the frequency of a sound wave. And frequency is 1 over the time period. So if this were in seconds, the frequency would be a cycle per second. So how many cycles do you get in a second? And that would be an example of frequency. So again, in this picture, wavelength, and that's shown by the red here, is the distance between identical points on consecutive waves. The amplitude, that's green, That's the distance between the origin and crest or trough. This is a trough, this is a crest. Frequency is the number of waves that pass a point per unit time. So if this is the point, you're counting how many waves pass per unit time. And here's an important equation that we get, that the speed or the magnitude of the velocity is equal to the wavelength, lambda, times f. Think about this. The frequency comes in cycles per second, or reciprocal seconds, because cycles is not a unit. And the wavelength is distance like meters, so this will be meters times 1/seconds, or meters per second, so that's the velocity. This is an important equation that we will use more than once. More written definitions, I guess. The amplitude of the motion, denoted by A, is the maximum magnitude of displacement from equilibrium. That is, the maximum value of the measure of x, if x is the direction of motion, is always positive. And the overall range of the motion is twice the amplitude, because it goes from a crest down to a trough. A cycle is one complete round trip from A to minus A and back to A, or from 0 to A, back to 0 to minus A, and back to 0. Motion from one side to the other, say from minus A to A, is a half cycle, not a whole cycle. Pay attention to this definition. The period, T, is the time for one whole cycle. It is always positive. The SI unit is the second, but is sometimes expressed as seconds per cycle. The frequency is the number of cycles in a unit time, is always positive. The SI unit of frequency is the hertz. 1 hertz is equal to 1 capital Hz. That's equal to 1 cycle per second. And since cycle really isn't a unit, it is 1 reciprocal second, s to the minus 1. This unit is named in honor of Heinrich Hertz, a great scientist. Often we talk about the spring system demonstrating periodic motion, because you'll pull it out, it'll bounce back and forth, back and forth, back and forth. And when we do, we're talking about a spring with force constant K. This was what we studied with Hooke's law, and that's the equilibrium position. Now, energy is conserved in simple harmonic motion, and so the energy is going to be the sum of the kinetic energy and the potential energy when you're storing something in a spring, for example. Now, this units are going to be joules, and we have not shown this mathematically, but it's true that this total energy, the sum of the kinetic and potential in simple harmonic motion, is proportional to the amplitude squared. It is 1/2 k, where k was the spring constant, times the amplitude squared. Here's some notes. So Vx and x are the speeds and position of the object at any arbitrary time in the motion. In simple harmonic motion, energy moves back and forth between the kinetic energy of the object and the potential energy of the spring. E is the total mechanical energy, which remains constant if there is no friction. That's the ideal case. Usually in a real world there is friction. And this is something that's even on ultrasound certification tests, and that is that the energy is proportional to the amplitude squared. I think we'll show you some examples of that later, but that's an important fact. Here's an example where we talk about ultrasound for medical imaging. So we'll look at the periodic motion of an ultrasound transducer. There's the transducer, and there's your patient. And so it's like an ultrasound loudspeaker that's used for medical diagnosis. The transducer is oscillating at a frequency of 6.7 megahertz. Now that is 6.7 times 10 to the 6 hertz. How much time does each oscillation take? And I'm going to leave off this angular frequency because that's getting into more trigonometry than we do. So the question we'll answer is, how much time does each oscillation take? Okay, so T is equal to 1 over F. And so that's time per oscillation. So it's 1 over 6.7 times 10 to the 6th. That is going to be 1.5 in scientific notation times 10 to the minus 7, which is going to be 0.15 microseconds. You should understand all of these. And the reflection here is that the transducer's rapid vibration corresponds to large values of frequency and small values of T. The reverse would be true for a slow oscillator. And as always, or as often is the case, there's a practice problem here if you want to practice it. Sometimes I draw exam questions from the practice problems. It's a little bit different. It says, suppose the transducer was adjusted so it oscillated with a period of 7.5 microseconds. What is the frequency? And you have an answer there. There's something you can check your understanding with. Now the equations for the position, velocity, and the acceleration involve a lot of trigonometry. So these really are trigonometric functions. And you can see that the amplitude is here and the cosine is a number between -1 and 1. So the maximum value there is A. The velocity, and this involves some math beyond what we cover in this course, but if you look at the velocity, it also is a trig function. You see A, but now you see the frequency appearing. And if you do the acceleration, you see the frequency squared appearing with A. A is in meters, F is in hertz, and omega, we're not worrying about omega in this course. So position, velocity, and acceleration all oscillate sinusoidally in time. That means that these are trig functions. The maximum value of the velocity and acceleration depend on the frequency of the oscillation. Now, idealized oscillation systems are frictionless, but real-world situations have friction and things get damped. The decrease in amplitude caused by these dissipative forces, such as friction, are called damping, and the corresponding motion is damped oscillation. The suspension system of an automobile is a familiar example of damped oscillation. The shock absorbers provide a velocity-dependent damping force. The direction of the force always opposes the car's up and down motion, so that when the car goes over or above, it doesn't just keep bouncing forever, it stops eventually. For optimum passenger comfort, the system should have enough damping so it bounces only once or twice after each bump. So as the shocks get old and worn, the damping increases and the bouncing is more persistent. And so that is bad. But so damping is an advantage for that kind of system. But a system such as a clock or an electrical oscillation system in a regular transmitter is desirable, has as little dampening as possible. So dampening is something that you should understand exists, and in more complicated math courses we do this, and we'll discuss this a little bit in terms of loss. So this is an example of an oscillator with a strong damping force. That means it started out going real big up and down, but then it goes slower and slower and slower as friction wears it out. If an oscillator has a weaker dampening force, the same signal will get damped out, but slower. So this graph shows damped harmonic oscillation for two oscillators, one strongly damped and one more weakly damped. We've talked about this, how waves can be, and we call this a transverse wave. Now in a transverse wave, the motion of the wave goes up and down perpendicular to the motion of the wave. So you see this wave is going up and down as you shake it along, and that means that the velocity of the wave is going this way, And so as the wave passes, each particle of the rope moves up and down and then down, transversely to the motion of the wave itself, perpendicular to. Those are called transverse waves. A longitudinal wave in a fluid, like really the sound waves, not measuring the pressure but measuring the sound wave itself, they go back and forth where they just push this. So as each wave passes, each particle, like it's a molecule of the median, moves back and then back and forth. And it moves parallel to the motion of the wave itself. So the wave's going this way, it's moving parallel. So there's a difference between transverse waves and longitudinal waves. But there are waves, such as this one, that can have transverse and longitudinal components as well. These are much more complicated, and we will not really be discussing those much in our course. This kind of ties the two motions together, but here is the spring. You push it down, it goes up and back and forth, and you can kind of see it's going up and down, or back and forth like this, but we're measuring this to set a rope going. This would be like the measure of the pressure. So we have the crest, the trough, the crest, and the trough. So this is longitudinal motion of a wave, but this is also mimicked and very much aligned with transverse motion. You can see the amplitudes listed here, the motion of the wave, that's the velocity of the wave. Remember, the velocity of the wave is the frequency of the wave times the wavelength. So the simple harmonic motion of the spring mass system produces a sinusoidal transversal wave on the rope. They're closely related. Now here we highlight again the relationship among the speed, wavelength, period, and frequency of a transverse wave. The wave advances a distance of one wavelength during a period of one period. So the wave speed, v, is given by v equal lambda over t. But because frequency is equal to 1 over t, the wave speed also equals the product of frequency and wavelength. So v, again, equals lambda f equal lambda over t. And the units of v would be in meters per second, f would be in hertz, or reciprocal seconds, and lambda is in meters. This equation is true for any wave, even those that are not mechanical waves. For many waves, v is determined by the properties of the medium. In such case, if the wavelength changes, then the frequency of the wave must also change to keep the product of the two constant. And so here again we see the longitudinal wave, the compression and the expansion. This is compression. Sometimes this is called rarefaction. But forward motion of the plunger creates a compression. This is the zone of high pressure. So if we're measuring the pressure, that would be a transverse wave backward, and it creates an expansion, which is a zone of low pressure. So again, you see how these two go together. You also see that a wavelength is the distance between corresponding points on successive cycles. Here's a problem for us to consider. A World War I infantryman sees the flash of a fired artillery gun, and 20 seconds later he hears the gun's sound. The speed of sound in air is about 1/5 of a mile per second, or 1 mile per 5 seconds, I guess. Which of the following is a reasonable estimate for the distance to the gun? So you see he heard it in 20 seconds. So it's A, B, or C. You would know what to do, but let's talk about it. The speed of light in air is roughly 1,000,000 times as great as the speed of sound in air. Thus, in this example, the time between the creation of the flash and seeing it from a distance of several miles is considered to be negligible. In air, sound travels 1/5 of a mile each second, or 1 mile in 5 seconds. So it would take sound 20 seconds to travel 4 miles. So the correct answer is C. A useful rule of thumb is that each mile gives a delay of 5 seconds. If you see a lightning flash and then hear the accompanying thunder 10 seconds later, the flash is about 2 miles away. Here's another example. Let's calculate the wavelength of the sound wave at 20 degrees centigrade of the frequency f is equal to 262 hertz. Now this is the approximate frequency of the note called middle C on the piano. And we're going to assume that the speed of sound in air is 344 meters per second. Well, we want to know the wavelength, and we know the velocity, and we know the frequency. And so we take lambda is equal to v over f. We're using that v equal lambda f equation. That's going to be 344 meters per second over 262 reciprocal seconds, and the seconds will cancel out. And you might want to look at those units to make sure you understand that, and we will get 1.31 meters. So the middle C wavelength is 1.31 meters. And again, there are practice problems that you can look at here. I tell you what is the frequency of the lowest note on a pipe organ and ask you to find the corresponding wavelength. There's an answer given here as well. Now, longitudinal waves, as we said, can occur in solids, liquids, and gases, but the wave speed is determined by the mechanical characteristics of the material. Ordinarily, the wave speed is proportional to the square root of an elastic factor, and also inversely proportional to the square root of the density of the material. These speeds vary depending on the material, and it also can depend on temperature. So let's glance at this again. I think we actually saw this before. The speed of sound in soft tissue is very close to the speed in water at 100 degrees, you know, we often use 1540 meters per second. But you see it has a dependence on the density as well as the stiffness of the material. Whenever two waves overlap, the resulting displacement of any position at any time is obtained by doing, hey, there it is again, vector addition of the displacements. So this can either be constructive, making a bigger wave, or it can be destructive, making it a smaller wave. Let's test our understanding of this. So two pulses are traveling in opposite directions on the x-axis. When they encounter each other, the net displacement of the superposition of the two pulses is 0. Which of the following things must be true? They are identical, but one is inverted relative to the other. They have the same width. They are traveling at the same speed. Well, for the two pulses to completely cancel each other out, they must be inverses of each other. Note the two pulses of the same width but differing heights would not cancel. The correct answer to this problem is A. They are identical, but one is inverted relative to the other. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. We are all in this together. May God bless you all.